Hello, my name is Cedici Martinez, and I'm going to share with you some work we're doing on integrating petrophysical data and geophysical modeling. I'll first start out with some background on the natural relationship between petrophysics and geophysics, and talk a little bit about geophysical inversion, which is one of the main tools we're using for integration. Then I'll give an example through the Stavely project of constrained and unconstrained inversion using petrophysics, and end with some conclusions and comments on the future. Starting with geophysics, the geophysical methods that we all know and love, like gravity, magnetics, and seismic, are sensitive to changes in specific physical properties of rocks. And I've put a table here just showing you those physical properties. So for example, the geophysical method of gravity is sensitive to changes in the density of different rock types. And petrophysics are the direct measurement of those physical properties. And since we'll be using geophysical inversion as our main tool, I'd like to talk about that. So let's first talk about our geophysical data. In the case of like gravity and magnetics, we typically use an airplane to collect that data. And this plane might measure an example shown here, which is airborne gravity gradiometry. And this type of data, there's 6 different measurements that we can obtain. And this is very similar to gravity, especially if you look at the TZZ component. However, most of the time we don't know what our subsurface geology is. And that's where geophysical inversion comes in. We're taking our geophysical data that we measure and trying to calculate or infer what the subsurface geology is. And in the case of gravity, because gravity is sensitive to changes in subsurface density, we can use geophysical inversion to obtain a 3D density contrast model like the one you see here on the right. And what we'd like to be able to do is to perform this geophysical inversion, but with some petrophysical constraints. After all, the petrophysics are direct measurements of the density we're trying to recover from geophysical inversion. And collecting this type of petrophysical information for studies like this is exactly what we're hoping the Mobile Petrophysical Laboratory will help. And the Mobile Petrophysical Laboratory is something we're putting together here at CSIRO in collaboration with the organizations you see there on the bottom of this container. And this will be a transportable container that houses the multi-sensor core logger from Geotech. And this multi-sensor core logger collects coincident measurements on core of different physical properties. And I've just put a list of those here. So the particular multi-sensor core logger that I've just shown you in the container was actually used to collect data as part of the Stavely project. And the Stavely project was a collaborative undertaking by the Geological Survey of Victoria and Geoscience Australia. And they collected a lot of different data, including petrophysics and coincident geophysical data. And so I'm actually going to use this to show you an example of integrating petrophysics and geophysics. So the data that I'm using, the petrophysical data, is from 8 drill holes that have density and magnetic susceptibility measurements using the MSCL. And I'm also going to use ground gravity and airborne magnetic surveys in the area. And I'm just showing you those here on the right. So in color, that's the magnetic data. There's 4 different surveys within the area that have line spacing ranging from 200 meters to 3,000 meters. And there's 7,246 gravity stations with variable spacing that you can see here in black dots. And this is just an example of the petrophysical measurements from one of the Stavely holes. And you can see here on the bottom, I've listed the different holes and the different depth intervals and the number of measurements associated with each hole. In collecting these types of petrophysical measurements along core, we can do this at a very dense sampling rate. And so this is just an example here where you see the measured magnetic susceptibility values in gray and different ways that we can summarize those measured values using, for example, the mode or the minimum and maximum value at a given depth. And this is one way that we're upscaling these petrophysics to actually use for constrained geophysical inversion. So what do I mean by constrained inversion? Well, it's easier to start out with explaining unconstrained inversion. Unconstrained inversion is just taking, for example, our gravity values and inverting them on a 3D model. Constrained inversion, we're taking the density measurements from the direct density measurements on core and using the minimum and maximum values to constrain our inverse model at those specific locations. So here you can see in the little box where our drill holes are, we're constraining our recovered model to recover a density value within our measured minimum and maximum value. And these are the two models obtained from unconstrained inversion of gravity and magnetic data. So on the bottom left is the density model from inversion of gravity data, and in the top right is the magnetic susceptibility model from inversion of magnetic data. And I've overlaid these on top of the geological model of the Stavry region just to give you an idea of what these different physical properties might be corresponding to. Now we've done a similar thing using constrained inversion, so using the petrophysics to constrain the geophysical inversion. And on the next slide, I'm going to show you a comparison of the unconstrained versus constrained inversion. So when we compare the unconstrained and constrained inversion, and here I'm just looking at the density models, we can actually start to see a change in our recovered density when we use reference or bounds constraint based on the petrophysical measurements. So what you're seeing here in the top left corner, this is the absolute model difference greater than 0.001 grams per centimeter cubed. And this accounts for about 0.55% of the total number of cells. But the unique thing here that you can see is wherever the boreholes are that we've actually used the petrophysics to constrain the model, you can see at depth, those model values are changing. And when we look across at different ways to constrain our density model, we see that the petrophysics are actually causing changes more broadly within our geophysical models. So it's really good to actually be able to include the petrophysics as constraints, even if they're only in smaller areas, because those do propagate changes into the rest of our geophysical model. Another thing we can do is take our unconstrained models and sample them at the place where we have petrophysical measurements. And so that's what I've done here. And this is just showing you an image on the bottom left of the unconstrained density model. And we're sampling it at all of the boreholes that you can see there. And cross-plotting the density contrast with the susceptibility. So based on those two different geophysical models, we can pull out those two different physical property values, and I'm just showing here in color the depth of those different cells. And we can compare that to the petrophysical data measured on drill core. So here I'm showing you cross plots of the density versus magnetic susceptibility in both of all of the Stavely holes in the region. And on the left, I've colored this by resistivity, and on the right, I've colored this by velocity. So here in the direct petrophysical measurements, you can already see trends within those different physical properties. And looking again at the geophysical models here on the left, we'd like to see if we can see the same trends in those models as we do in the petrophysics. So keep in mind here on the left, all we've done is sampled our geophysical models at the same locations that we have core measurements. And so here, because our geophysical models are regional, we have fewer data points from those geophysical models to compare to the petrophysics. But it is interesting here that we see the geophysical models at least lying within the same trends as the petrophysics. So overall, I've shown you a couple of ways that we're looking at integrating petrophysics and geophysics. Obviously, there's multiple factors to consider when doing this and various ways to actually do this type of integration. Now, we're just looking at using geophysical inversion, and some of the conclusions that we've come to so far is that incorporating shallow petrophysics into the inverse modeling changes the recovered models at depth and propagates those changes further out into our geophysical models. And one of the things that we're looking at now is whether or not there's value in understanding the trends in the petrophysics and the geophysics. So instead of just looking at a comparison of the petrophysical values to the geophysical models, can we pull out trends in our unconstrained geophysics that we see in our petrophysics? Thank you for your time today, and if you'd like to know more, feel free to get in touch. Here's my email address and our website. Thank you.